Let's do a quick review of the two labs that we've done. In the second lab, we took an object and placed it in front of a lens, and then we found the image of that object. We measured the distance between the lens and the image, and the distance between the lens and the object. And then we found that those numbers followed this rule, that the inverse of the image distance was 1 over the focal length of the lens minus 1 over the object distance. This is normally written like this, and is called the thin lens equation. In the first lab, we took the light from the sun and had it strike a lens. We found that then the light focused itself together and then continued on. Okay. So we called this distance here between that point where the light focuses and the lens the focal length. Okay, the same thing that goes into this equation here. Now the question is, can we reconcile these two observations? Are they really the same thing, or are they just different laws of nature? Now before we do that, we need to make one other observation. So do this now. Get your converging lens, the thickest one, and your cell phone, and turn on the flashlight on the cell phone. Okay, so put your flashlight close to the lens. So it's really close. The light will spread out from there and hit the lens, and then it will spread out and make a dot on the wall. So make it close enough to a wall or something so you can see maybe a meter away. Okay, so you should see a big circle over there. Now, what we're going to do now is we're going to slowly move the flashlight further away from the lens. As you do so, you should find that this circle over here on the wall will shrink. At some point, you'll find that the light goes straight forward, and this circle of light is the same size as the lens. At that point, the light bulb of your flashlight is at the focal point of the lens. Okay, so we're going to try to look at it in this slightly different way and learn something similar to what we decided up here in this diagram. Okay, and then the rule goes like this. If light comes from the focal point, it goes out parallel to the axis of the lens. This is useful for making a flashlight, for example. A flashlight, if you want to have a beam, maybe you've had one like this before where you can actually adjust something and it changes the size of the beam. What you're really doing was moving the light bulb relative to the lens. Okay. If you've seen one of those searchlights before where they have some kind of event, they shine a light up into the sky, it's essentially the same thing. You have a very bright light with a lens, and it makes all the light, instead of spreading out, it all goes forward along this path. It keeps it from spreading out. Okay, so that's another observation. If light comes from the focal point and hits the lens, it all goes out parallel. All right, so we're going to write these down together because these kind of rays are principal rays. So we'll start with that one, just so we're familiar with it. Light comes out from the focal point and goes forward. The other one that we did before was light comes in parallel to the axis and it goes through the focal point. The third one, which we haven't talked about, is that if light just goes right through the center, heads right towards the center, it actually doesn't bend at all. It just goes straight through. You can think about that because right here in the middle, the sides of the lens are parallel, so it's really just like a window, and we know that windows don't bend the light. So these are the three principal rays. Coming from the focal point goes out parallel, coming in parallel goes through the focal point, and then the light that goes through the center of the lens is undeflected. Now we're going to use these principal rays now to try to construct an image. So we put an object here and a lens. We draw the lens now as just a line just to make it easier. That equation we had before was called the thin lens equation because it ignores the thickness of the lens actually. Okay, so we're going to draw it as a line, but this is a converging lens. So let's just go ahead and start. So let's take the light that's coming from here. Now, of course, light goes in all directions, but we're just going to draw the principal rays, the ones that we know where they go. So the light that comes off in that direction, we know has to go through the focal point. Okay. The other nice one is if it came like this and came through the focal point, then we know it has to go out parallel. And then, of course, the simplest one is right through the middle. That has to continue in a straight line, like that. Now notice that all of them meet in the same place, and that's actually the location of the image. Now, the other rays that leave from here also hit the lens. They're not one of the principal rays, so we wouldn't really know where it was going to go. But we know that it has to go in the same place as the other one, so we just draw it so it does. Should use a different color for that one so we don't get it confused. So any other light that hits the lens will also have to go through the focal point. Okay, but any two of the principal rays will allow us to find the location of the image. Now we're ready to answer our question about can we reconcile these two observations about the lens. The lens is the thin lens equation and this following of rays. So what we're going to do is we're going to redo this problem, this thing here. And see if we can't find the thin lens equation. Now, I've colored in some of these triangles, so it's the same diagram. You can see the three principal rays. Okay. But what I've done is I've colored in some of the triangles, and I've colored in 4 triangles in 2 different colors, and hopefully you can see that the 2 green triangles are similar triangles, and the 2 pink triangles are also similar triangles. So let's label some distances now on here. So we know that this distance here this is the lens, right? The object's over here, and the image is over there. Okay, so we know that this is the object distance. This is the image distance. This is the focal length. And this is the focal length. Okay, so apparently this is the image distance minus the focal length. And this is the object distance minus focal length. Okay, the other thing we're doing is we're going to call this thing HO is like the size of the object. We're going to call this minus HI for a reason that won't be obvious for a while. But we want the positive distance, and HI is pointing downward, so it's a negative quantity. If that makes sense, this will end up making things easier. But here in the algebra, we need to use minus HI because HI is negative. Okay, so in order to do these similar triangles, we need a positive quantity. All right, so let's go ahead and draw some of these out. Let's start with the green one. Okay, so we could do this. We could take HO. Then that should be equal to the ratio of the other green triangle. Okay. And let's do red one here. So we have HO over DO. I'm going to rewrite these just a little bit. So we're just going to do some algebra now. So this is minus HI over HO. And this F over DO minus F. And I'm going to write this in the same way. I could have started with this, but that's a harder one to write down. Okay. We've already gotten something here which is useful. This guy is called the magnification equation. You can see it gives the ratio of the image side to the object side. So if it got bigger, that number would be a big negative number. All right, but we want to combine these. So this is the reason I did these. You can see they both are equal to minus HI over HO. So that means the right-hand sides have to be equal. So okay. Just get rid of the fractions. I'm going to multiply both sides by this and that. So what we end up with. Now, I'm going to make this look worse by dividing both sides by the same thing. Okay, so I haven't really done anything. I just divided both sides by FD0 dO di. Now, that seems like a bad idea, but notice that almost everything cancels. Okay, so in this one we just get 1 over di. On this one we just get 1 over f, and this is 1 over do. Okay, the rest of it cancels, which, lo and behold, is our thin lens equation. Okay, so remember what we did? We constructed this diagram using the principal rays. So it's a geometric construction of where the image is. But then by using similar triangles, we were able to, and with a bit of algebra, we were able to show that a thin lens equation has to be true. So that's a nice result. All right, now this is actually going to help us because if you remember, in the second lab, for some locations of the lens, we couldn't find any image. Okay, it ended up, that happened when the object was closer to the lens than the focal length. So it's inside the focal length of the lens. So now, just because you didn't find an image doesn't mean that our principal rays don't work. So let's try this. Let's go ahead and find these. So we take the one that goes out parallel. Where does that go? It goes towards the center, or towards the focal point on the far side. So that one's nice. You could also do this one through the center of the lens. Now, notice that those aren't coming together. They're diverging from each other. The other one is a little harder to draw because the light doesn't actually start from here. But if we take a line, it's a guiding line. I'm going to make it thinner. All right, then we can see where we need to go. So the lens doesn't know that our ray didn't really come from that focal point, and it doesn't care. All it cares is the direction it's going and where it hits. So that one will go out that way. So those are our 3 principal rays. Now, they don't converge on the right. They're not coming together. So if we put a piece of paper over there, we're not going to ever find an image. But they do converge on the other side. So let's follow them backwards. So we have to extend them from the lens. Okay. So we see that the image is here. We call it virtual because it's not actually there. It's virtually there. Somebody looking at this from over here, if they're looking at that lens, it would appear that the object is back here. That's what the rays of light are telling us. Okay, so it's virtually there, but there's no light there. If you put a piece of paper over there, you're not going to get any light at all. Now, let's see how this works with the math, because it seems like something weird is going on. How could the same equation work for both sides? Now let's just let's assume that these squares on this image are 10 centimeters. So that would mean this distance is 60 centimeters. And this one's 40. And this one's 120. Okay, so the object distance is 40. So let's try calculating this. The focal length, well, we know what the focal length is, it's 60. And the object distance is 40. So we can see where the issue is here. If get a common denominator, so this implies that the image distance is minus 120 centimeters. So this is nice. It tells us we actually get this 120 quite easily. So that location, the negative, tells us it's on the same side that the light came from. So it's before the lens in a sense. So if you think of that light is going through the lens, it's on the side before the light hit the lens. So that's the significance of this minus sign here. And the thin lens equation gives us that. Okay, so it's the thin lens equation is very nice in that way. The other thing we notice is that, what about HI? It's positive here. Both of these are positive. So if we look at the magnification equation, we see that the ratio is a positive number this time because they're both upright. And sure enough, this one is 3 times taller. The image is 3 times taller than the object. Okay, so both the magnification equation and the thin lens equation are both perfectly fine as long as we remember to use the negative numbers. So negative distance means on the light side of the lens, so before the light and on the side before the light enters the lens. All right, so now I want to remind you of the other thing we did in the first lab was the diverging lens. So in that case, instead of the parallel rays converging to the focal point, they converged away from the focal point on the incoming side. This could also be written in terms of principal rays. Okay, so we have the one going straight through the center. We have the one diverging away from the focal point. The third one is just like we showed with the converging lens, it works both ways. This one, if you come in now towards the far focal point, it actually leaves parallel. So those are the 3 principal rays for a diverging lens. They're a little different. Okay, let's do the same thing and try to construct an image with a diverging lens. So let's do the same thing here. We got an object, a diverging lens, which again I'm just drawing as a line. So here's our lens. All right, so let's try the 3 principal rays. So we start with this guy. It has to travel out as if it came from the focal point. So we'll go ahead and draw that guiding line first, and then we'll add to it where the light actually goes. All right, then we have the easy one, the one through the middle. Okay, so we can already see where the image is. We see these two rays here. They don't converge on the right, but they do converge on the left. So sure enough, the image will be here. It is also a virtual image. I suppose this one beam actually does come from it, but the rest of them don't. Let's go ahead and add the third principal ray just for good measure. So we do the same thing. We add a guideline first. We go from here towards the far focal point. Then we follow that. Get the wrong size here. We follow that until we hit the lens, and then we go out parallel. And then, sure enough, if we follow that backwards also, it goes back to there. Let's do the same thing again with the math of it. So this is 100. This is 120. The image distance is negative 40. We know it's got to be negative 40 because it's on the left-hand side. Okay, so let's try doing this the other way. Let's just solve for 1 over f. So the object was 120. The image was negative 40. This is so apparently the focal length is negative 60 centimeters. Okay, so this is nice. And sure enough, this where's the focal length? It was at 60, yeah? Okay, this is one of the more confusing things about lenses, but it's not so bad, really. You just have to remember that for a diverging lens, you have to use a negative number in the thin lens equation. Okay. So let's remind ourselves of the sign conventions that makes the magnification equation and the thin lens equation work. Okay, so we can have negative values for things. Okay, the image is negative if the image is before the lens. The object, on the other hand, is negative if the object is after the lens. Now, it's not obvious how that could be possible, but we'll see on Friday how we can do that. The heights are negative if it's downward or below the axis. And the focal length is negative if it's diverging. Okay, so that's pretty much it for lenses. There's another thing that I'd like to talk about here. We left over from Snell's law. And it's called total internal reflection. Now, you remember Snell's law. it told us how light bent when it went into a different medium. So we have the incident ray and the reflected ray off the surface. Here's our surface. And then the part that's transmitted into the refracted part, which goes into the material. And depending on the index of refraction of each, the angle is different. Now, let's think about tracing this backwards. So suppose we saw the light coming down in this transmitted part here, and we decided, okay, let's go put a mirror there or something, or get a little laser and fire the light back at the same angle that we found it. So now this becomes the incident wave. The question is, where does it go? Well, it ends up that algebraically, if you look at the thin lens equation, we had Ni sine theta I right up above. And d sine theta t. It's totally symmetric. In fact, it doesn't really matter which is transmitted and which is incident. So why don't we just call them 1 and 2? Okay. So the only thing is you need to make sure that you use the index of refraction that goes with that angle on the same side of the equation. And so of course it's going to be the same angle, so this should go back in the same direction that it came in over on this side. All right. So this generally works for light, that light is reversible. So if a beam of light can go one direction, it can easily go back on that same path in the reverse direction. The one thing that is different is that the reflected part, of course, is this way. Now, but there's something interesting that happens here. We're dealing with a case where the gray region has a higher index of refraction. And so let's go ahead and solve for the transmitted angle. I'm going to do it like this. Now the sine of that angle, theta I, is always less than 1. Sine of the angle goes between 0 and 1. So this transmitted angle has to be less than or equal to the inverse sine of just that ratio. Okay, so we call the inverse sine of that the critical angle. One way to think about this, which I think is the clearest, is to think, what if theta I was 90 degrees? And the sine of 90 degrees is 1, and it goes poof and vanishes. Okay, now it's a little bit weird to think of 90 degrees, but what does that mean? It means the light's coming in parallel to the surface. So you can't really quite do that, but you can get close. And in that case, the light goes out here at the critical angle. Now, the important thing is, no matter what the incoming incident angle is, the transmitted angle is always less than that critical angle. We just proved it. So in other words, no matter what the incident angle is, you never get angles of light over in this region here. So that leaves us with a question. Now let's draw that critical angle on here also. what happens if we send in light backwards? Okay, so this is beyond that critical angle. I guess I should really do it on the other side. Okay, so we send light in here. Where does it go? Well, the reflected part is fine. That doesn't change. But it ends up that there is no transmitted light at all. All of it is completely reflected inward. So this is called total internal reflection. Any light striking the surface at an angle greater than the critical angle, this is the critical angle here. If you have an angle greater than the critical angle, it just bounces off the surface with none of it transmitting through. This is actually used to good advantage in fiber optic cables. It's just a fiber optic cable is just a very thin strand of glass. And so if you send light into it, it bounces back and forth inside the glass, but it can't get out. In fact, there are cables going all over the oceans, sending signals back and forth. So all the internet and stuff that crosses the ocean goes through these fiber optic cables. So for example, up on the coast, Northern California, Manchester, there's a cable that leaves there, goes all the way across over to Japan. These are just some of the cables in the Pacific Ocean. So these are all fiber optic cables crossing the whole way. There are repeaters along the way, but not that many. So it's something to boost the signal a little bit higher. So you can send a signal from one end, goes all the way across the Pacific Ocean, comes out the other end. And that's just because it has to bounce back and forth inside the cable. I want to show you one other thing that you could actually do yourself. Maybe next time you go to the swimming pool. Or if you want to do it, you can stick your phone in a bowl of water if it's waterproof. So I took a triangle that has a ruler on one side, and I stuck it into water. So it's just a mixing bowl. Okay, so it's just sticking into the water. And then I put the camera, actually I couldn't put it inside because my camera isn't waterproof, but I put it on the side of the bowl, kind of looking up at about a 45-degree angle, so it could look in through the side of the bowl, like looking into a fish tank. And this is what you see. Now it's going to be a bit confusing, so bear with it. So this is what you see looking up. So it's not easy to sort out, but let's have a go at it. The easy part to understand is this bottom part. So I'm going to draw a line here separating out two regions. This part down here is just the camera looking at the ruler underwater. Okay, there's no bending involved. That's this green line down here in this diagram. So this region here is just the camera looking directly at the ruler. So nothing strange happening there. All right, now there's another line up here that's dividing two behaviors. So let's look at the top part. The top part, if you can look carefully at those numbers, you can see there are 2, 3, 4, 5, 6, 7, 8. They're kind of blurry because the camera is having a hard time focusing. But what that is you're seeing the ruler above water. And in fact, this part of the ruler, if you look, it goes up to 9.5, and then down here, there's 9.5 here, here's 9.5 there. Those two actually join together. Okay? So what this is the fact that why we're seeing them separated is that in order to look at this part of the ruler, which is above the water. You're looking out of the water. So this whole part up here is looking out of the water. So you look up at the surface of water, you're looking at what's outside the water, and you see the ruler. The interesting thing is that in order to see the 9, you have to look up higher than you would normally. You don't look just above where you see the 10. Okay, because you see the 10 over here, right there, but you see the 9 by bending light. Okay, so it appears to be higher. You have to look up here, and from your point of view, you think the 9 is way up there where you'd expect to see the 4. Okay. So that's just refraction. Now this other part in the middle, if you look at it carefully, you can see the numbers are backwards. So this is actually a reflection. So that's the internally reflected part. Okay. So that's this sort of pinkish color here. It hits the surface of the water, gets reflected, the light comes from the ruler, hits the surface of water and goes to the camera. So that's why it's inverted, because it's a reflection. This is kind of fun, the swimming pool, because if you go to the bottom of the pool and look up, you'll see right above you there's a circle at about a 45-degree angle where you can see out, and you see everything. You can see from one edge of the pool, the coping on one edge to the coping on the other edge. But it's up in a let me draw a picture. Swimming pool with water. Hopefully it has to be fairly still. So here you are, laying on the bottom, looking up. So if you look here, what you're seeing is light being refracted down from the edge of the pool. So you see this edge of the pool, maybe there's a drain or something. If you look straight up, you see whatever's up there. Maybe there's a bird flying by, so you see the light from the bird. If you look in this direction, you see something over there. Okay, same thing on this side, you'd see the things out on that side. So that's like a circle on the top of the water. But outside of that circle, it's a mirror. But the mirror is the surface of water, so it sort of looks like maybe you've never seen a pool of mercury, but it looks like a pool of mercury. You'll probably think more like something out of a movie. Yeah, so a liquid metal. And what you'll see in that mirror is what's under the water. So give it a try if you have a chance. You could try it in your bathtub too if you have one. Put on swim goggles, lay down and try to look up. Fill it as deep as you can get it. I suppose, again, you could try putting your phone there if it's waterproof.